An analysis of the potential for the formation of nodes of persisting complexity. By Nick King and Ala Jones. Global Sustainability Institute, Anglia Ruskin University, Cambridge CB11PT, UK. Academic Editor, JinHyo Joseph Yun. Abstract. Human civilization has undergone a continuous trajectory of rising socio-political complexity since its inception, a trend which has undergone a dramatic recent acceleration. This phenomenon has resulted in increasingly severe perturbation of the Earth system, manifesting recently as global-scale effects such as climate change. These effects create an increased risk of a global decomplexification, collapse, event in which complexity could undergo widespread reversal. Nodes of persisting complexity are geographical locations which may experience lesser effects from decomplexification due to having favorable starting conditions that may allow the retention of a degree of complexity. A short list of nations, New Zealand, Iceland, the United Kingdom, Australia and Ireland, were identified and qualitatively analyzed in detail to ascertain their potential to form nodes of persisting complexity. New Zealand is identified as having the greatest potential. The analysis outputs are applied to identify insights for enhancing resilience to decomplexification. 1. Introduction. 1.1. The Human and Earth System Predicament. The globe-spanning, energy-intensive industrial civilization that characterizes the modern era represents an anomalous situation when it is considered against the majority of human history. Several large revolutions in terms of population, total size and rate of change, social organization and patterns of energy and other resource use have occurred to bring about the modern world. The first major change that humans achieved after a long period, approximately 3 times 105 years, of living in small, dispersed bands of hunter-gatherers was the transition to an agriculture-based civilization, which occurred independently in multiple locations. This was enabled to a large degree by the shift approximately 1 times 104 years ago to a warmer, more stable interglacial climate at global scale that has been characterized as the Holocene. 1. The major shift resulting from the spread of agriculture led to consistent energetic and material surpluses which, in turn, allowed for the establishment of fixed urban settlements, hierarchical societies and organizational complexities such as labor specialization. The emergence of these phenomena set in motion enhancing feedback mechanisms, for example, food surpluses, that led to increasing populations and the spatial expansion of agriculture and human activity over the majority of the Earth. 1. The growth of the extent and complexity of human civilization continued for centuries but was ultimately constrained by reliance on natural flows of energy, primarily insulation captured through photosynthesis and the availability of biomass in which it was stored, and the application of human/animal muscle power to utilize energy and material resources. Overcoming this limit commenced from approximately 1800, the start of the Industrial Revolution, through the large-scale exploitation of the very large energy stock contained within fossil carbon deposits using newly developed technologies. This set in motion new enhancing feedbacks, for example, coal-fired pumps which allowed previously inaccessible coal seams to be mined, providing further energy for industrial development. 1. The global population and industrial capacity grew rapidly for approximately 150 years but achieved near exponential growth only from approximately the middle of the 20th century. This period, characterized as the Great Acceleration, 2, has generated the most rapid and profound of all the changes described above, resulting from the strengthening of the feedbacks initiated at the start of the Industrial Revolution. The Great Acceleration is characterized by substantial and ongoing increases in societal complexity and the extent and intensity of human activities across a broad spectrum of measures including, but not limited to, population growth, energy and freshwater usage, nitrogen fixation and cement production. The aggregate effect of this dramatic growth has been the strong and increasing perturbation of the Earth system and the biosphere, making collective human civilization a major force acting at global scale. This has led to the characterization of recent Earth history as the Anthropocene, 2,3. From a biophysical perspective, human civilization is a non-equilibrium thermodynamic or dissipative system that must maintain a minimum level of available exergy to avoid entropic decay and a yet higher level to permit physical growth. 4. From the ecological economics perspective, it can be viewed as an economic superorganism that seeks to maximize energy consumption through self-organization at a large scale. 1. or the megamachine driven to ever greater size and scope by the enhancing feedbacks of capital accumulation. 5. The Earth system is, however, finite in spatial extent, energetic capacity and overall complexity, and the ongoing expansion of human endeavors has and will continue to result in the Earth system's limits being exceeded and the system being moved out of equilibrium. The Earth system, characterized as Gaia, is a self-regulating mechanism. 6. And observable shifts in the behavior of Earth systems may be manifestations of balancing feedbacks resulting from the strong and growing perturbation from human activities. These may have the potential to fundamentally undermine the agriculture-based civilization that has flourished in benign Holocene conditions. The threats to the ongoing and future viability of globalized civilization have been the subject of academics, popular science and literature at various points in history, but this subject area has garnered particular attention in recent years. The following subsections describe the most significant of these effects and why they might be significant for the predicament of human civilization. 1.2. Literature Review of Global Environmental Threats. The following subsections describe 4 major categories of threats to the ongoing viability of the high-intensity civilization that has emerged from the Great Acceleration. These phenomena are the encountering of limits, diminishment of returns, ecological destruction, and risk multipliers. These are discussed in detail in the following subsections. 1.2.1 Encountering of limits. The limits to growth studies, 7,8, were seminal in that they first applied global-scale modeling to human population, the industrial economy and global biophysical limits and identified the potential for future collapses of human population and welfare to occur. Recent reanalysis, 9, suggests a strong correlation between the characteristics of worst-case modeling scenarios and real-world trends for the early 21st century. A recent calibration of the Limits to Growth World 3 model with real-world data, from 1995 to 2012, 10, identified some departures between the model and reality, although the broad findings held true. Despite the differing interpretation, the findings remain highly compelling and have inspired more recent work, 11,12,13, which reapplied system dynamics models to the economy-environment system and identified the Seneca effect, in which collapses might occur over short timescales. Other attempts to describe the encountering of global-scale limits include the Planetary Boundaries Framework, 14, which defines the Holocene's biophysical conditions in which civilization developed and flourished as having boundaries for stability. 9 separate boundaries are defined, 3 of which, biodiversity loss, the nitrogen cycle and climate change, have been transgressed. Further transgression may risk moving the Earth system to conditions inconducive to supporting large human populations. Another study, 15, combined the Socioeconomic Sustainable Development Goals, SDGs, with an integrated socioeconomic model of global human activity/biophysical model, Earth 3, to conclude that meeting the SDGs cannot be achieved within global environmental limits. The studies described above consider the holistic, systemic viewpoint, but numerous studies also provide underpinning evidence for limit transgression with a narrower focus on resource depletion. The decline in production experienced, 16, in multiple major oil fields worldwide and the low rate of discovery of large, new hydrocarbon sources in recent decades has significant implications for constraining key societal functions such as mass logistics. The peak use rates across multiple crucial resource types shows that numerous resources had a synchrony of peak use centered on the year 2006, 17. The phenomenon has implications in terms of the capacity of global society to adapt to physical scarcity given that limits on the availability of multiple resources may have to be managed simultaneously, and this may constrain the capacity for substitution and decoupling of resource use. 1.2.2 Diminishment of returns. Energy Return on Investment, EROI, 19,20, is a measure that has utility as a fundamental measure of the minimum energy that is required to support continued economic activity and social function. Expanding on this, 21,22, the availability of high ROI energy sources, that provide an excess of energy, can be linked with socio-economic complexity and higher societal functions, for example, education, health care, culture, that are indicative of higher living standards. Traditional fossil fuels have provided a high ROI value for many decades, but the decline in the quality and accessibility, and therefore ROI, of these fuels, in parallel with the generally lower net energy provided by other energy sources, could result in a reduction in global economic output and quality of life, 23,24,25. This is supported by the Medeus model, which indicates that a transition to an energy system with a high proportion of renewables may lead to an energy trap, 26. Together, these studies indicate the crucial role of abundant, high ROI energy sources in maintaining societal functionality and growth, which contrasts with much of the extant economic worldview, 27. The excess of energy provided by high ROI energy resources has also provided the conditions for the enhancing feedback mechanisms of capital accumulation to permit the accumulation of wealth by subregions and populations of the world. Evaluating, 28, this phenomenon quantitatively through the application of predator-prey population dynamics models to assess the evolution of four factors, elites/commoners/nature/wealth, identifies that, economic, elites preying on resources and the labor of commoners can lead to economic stratification and ecological strain and, ultimately, irreversible societal collapse. Applying, 29, qualitative arguments demonstrates that the affluent proportion of the human population have disproportionate global environmental impact, resource use and pollutant emissions, but cultural factors, wealth accumulation, consumerism, etc., make the necessary changes to lifestyle unlikely to occur. Sociopolitical complexity has been fundamental to the functioning and success of human societies post the agricultural revolution, 28, and is described as the collective problem-solving and efficiency-seeking strategies deployed by all organized human societies in response to encountering problems, constraints, for example, energy or water, or aspirations. It may include bureaucracy in the form of governments, specialization of roles, occupations and industries, new technologies, and increased mobility and trade. The sociopolitical complexity, 30, hereafter complexity, provides marginal gains, i.e., net benefits, when initially deployed, but as further complexity is added, the marginal gains diminish in an inversely proportional manner. The subsequent progression through zero and then negative marginal benefit is posited as the factor consistent with societal collapses, in varied locations and timeframes, throughout history. Applying simple system dynamic models, 31, mind-sized, 11, demonstrates the tendency for complexity to peak and then diminish. Modern, globalized civilization is characterized by extreme levels of complexity, which has the potential to introduce additional risks. For example, nuclear technology, 32, in the context of its development and the externalities, highly hazardous redundant facilities and long-lived waste that require highly controlled management, that it generates demonstrates the particular risk of such high-technology solutions in that they beget and lock in the need for further complexity through the generation of egregious externalities. Any future reduction or loss of supporting complexity could result in widespread harm in the future if the persistent hazard that has been generated ceases to be manageable. Modern complexity, 33, of the sociopolitical type, but also technological and informational, may have reached such levels as to have likely become largely and effectively indecipherable by individual humans, and human agencies and institutions. This may be manifesting in phenomena such as unpredictable behavior in stock markets, frequent failures in the implementation of megaprojects and the failure to address global-scale challenges. 1.2.3 Ecological destruction. There are a total of 5 extinction events evident in the geological record which have been attributed to several natural events and causes, for example, rapid climatic changes, flood basalt eruptions, bolide impacts, 34. The 6th extinction episode, or alternatively, the Holocene extinction event, is currently ongoing, 35, meaning that Earth's biosphere is currently under pressure at levels which occur only infrequently even over geological timescales. This loss of biological diversity is one of the most severe human-caused global environmental problems, 35, particularly with the advent of the Great Acceleration. The short timescale on which these impacts have grown, along with their sheer scope and extent, has resulted in less than 3% of the world's land surface area remaining as fundamentally intact, i.e., with species diversity and habitats unaffected by human activity, 36. The large-scale perturbation of ecosystems as the 6th extinction event progresses is likely to have severe global consequences, with the provision of vital ecosystem services likely to severely reduce as effects cascade at global scale, 35. The growth in human populations and technological development can be linked, 37, to resource consumption, and the propensity for humans to destroy forest ecosystems gives a high probability, greater than 90%, that global civilization is very likely to suffer a catastrophic collapse in future, within a few decades. The current extinction event also differs in that it is driven by the concurrence of phenomena unique to human actions including changes in land and sea use, direct exploitation of animals and plants, climate change, pollution, and invasive alien species, 38. It is also characterized by unique Anthropocene features, such as the introduction of a global plastics cycle, 39, which pose an as yet unknown threat to the stability of global ecosystems, and by extension, complex human civilization. 1.2.4 Risk multipliers. There are several phenomena which are emergent from the summation of human activities and the resultant perturbation of Earth systems which serve as risk multipliers that are likely to exacerbate existing trends and feedbacks. Climate change is likely to be the most pervasive of these risk multipliers, largely because the climatic system is planet-spanning and interfaces directly or indirectly with human and natural systems in highly complex ways. Climate change can be described as a hyperobject, 40, which are entities that have spatial and temporal scope and dimensions far beyond that of the human realm. The human system, when considered as an economic superorganism, 1,5, a decentralized, energy-consuming structure that is emergent at global scale, may also be continuous with the climate hyperobject given that it excretes greenhouse gases. The self-organizing tendencies of these hyperobjects, which seek growth even where biophysical limits and environmental destruction constrain them, means that the prospects for reduction and reversal of greenhouse gas emissions are limited and accelerating feedback mechanisms, 41, have the potential to exacerbate this tendency. It is possible to provide a qualitative framework, 42, to identify which key underpinning societal functions are most likely to be subject to amplifying effects, particularly in relation to conflict. Although the direct link between climate change and past and present conflicts is uncertain, there is support for the potential of climate change to introduce instabilities. It is within this context that climate change has been ascribed a near certain potential to severely disrupt human civilization, 43, particularly in light of the potential for tipping points and nonlinearities to occur within the climatic system, 44. Pandemics present another source of risk multiplication given their long history of strong feedbacks on human population dynamics and economic activity, 13. Several studies made prescient links between destructive human activities, such as deforestation, and pandemic risks, which have been borne out by the COVID-19 pandemic of the early 2020s, 45, 46, 47. The potential threat of coronaviruses, 45, was known to pose a risk to human populations, particularly with bats as a vector, due to the nature of their virome. The political, economic, financial and social impacts of the COVID-19 pandemic are not yet understood given that it remains ongoing as of 2021 but are likely to be far-reaching and long-term given the broad-spectrum effects on various aspects of societies across the world. Furthermore, the United Nations, 48, warns that future pandemics may be more severe than COVID-19 in terms of virulence, fatality rate and other impacts. The risk of infectious disease crossover due to ongoing human encroachment into remaining wild areas of the planet, combined with unpredictable societal impacts clearly demonstrates the cross-cutting risk presented by pandemics. The risks arising from the extreme complexity and interconnectivity has developed as human society has grown and evolved through to the modern era, 49, 50. Civilization comprises an agglomeration of human and natural systems that interact in highly complex ways, and as such, there is an ever-growing probability that the smooth operation of the vital functions that underpin societies may be disrupted in the future. The increasing hyperconnectivity of the globalized economy, 49, is a process characterized by the reduction in system resilience in favor of increased efficiency and complexity, which may increase the risk of initially small disturbances being subject to enhancing feedbacks that spread and potentially eventually create system-level threats, the butterfly defect. An alternative viewpoint, 50, is that complex, integrated societies have a natural resilience to a range of stresses and shocks, i.e., that they tend to self-correct when internal and external shocks occur, for example, as seen in the response to the global financial crisis. However, Perturbation in excess of tipping point thresholds can create propagations leading to major changes in the state of such systems. Whether the propagation of systemic risks is subject to threshold effects or has the potential to build from even minor disturbances, the risks of large-scale failures due to increasing globalization, complexification, interdependency and the speed of fundamental societal support systems, particularly in the more developed regions of the world, creates significant global risks. This is particularly acute for the proportion of the human population that is entirely reliant on systems such as automated wastewater management and industrial food production, i.e., large urban populations. Furthermore, the global system may now have moved beyond human control or understanding, 35, and may therefore be even more prone to catastrophic behavior modes that can propagate in coupled systems through a range of unpredictable mechanisms, 51. This creates an interconnected global system that fails to adequately understand the nature of these complex, dynamic systems, 52. 1.2.5. Societal collapse. Overall, the literature sources summarized in the preceding subsections paint a picture of human civilization that is in a perilous state, with large and growing risks developing in multiple spheres of the human endeavor. The synthesis of the conclusions presented in these myriad studies is that 70 years of the Great Acceleration, plus the lesser but cumulative effects of the preceding approximate 10,000 years, have had indisputable, egregious effects on the functioning of the totality of the Earth system, and the continued trends and behaviors of the human collective look highly likely to exacerbate these existing trends. The potential for nonlinearities and other complex system effects only serve to potentially heighten the risks and consequences. This can be summarized as 53. Future environmental conditions will be far more dangerous than currently believed. The scale of the threats to the biosphere and all its life forms, including humanity, is in fact so great that it is difficult to grasp for even well-informed experts. This statement effectively sums up the current situation for humanity and indicates that it may be increasingly likely that the current, and near future, timeframes represent a significant inflection point. Changes of varying magnitudes are possible in the coming years and decades, up to and including the collapse of organized societies. Various scientific and popular literature sources have explored the concept of societal collapse, with an increase in these descriptions occurring in recent decades as awareness and concern regarding the global environmental predicament has grown. Table 1 summarizes the key features of the most significant of these conceptual descriptions. 1.2.6. Collapse lifeboats. In line with the studies that have explored the concept of societal collapse, a number of studies in the scientific and popular literature have developed the concept of collapse lifeboats. This generally describes locations that do not experience the most egregious effects of societal collapses, i.e., as may occur due to the effects of climatic changes, and are therefore able to maintain significant populations. These studies have considered small, isolated communities, 58, in larger countries including Australia and New Zealand, 54. The concept is therefore an extrapolation of societal collapse, in that it considers events, features and societal structures that might feasibly develop in the context of a collapse. Extrapolating the impact of warming due to climate change has been a particular focus for some of these studies. It is possible to explore the potential economic, social and ecological conditions prevailing in the world at each degree increase in the global average temperature due to climate change, from 1 to 6 degrees Celsius. It is within the 5 degrees Celsius increase scenario that the potential for major relocations to particular regions of the world can result in a reversal of globalization, 59, which in turn causes economic depression and shifts in global populations. The British Isles, Scandinavia, Patagonia, Tasmania and the South Island of New Zealand are identified as locations that migrants may seek to relocate to in this scenario. With the global average temperature increased by 4 degrees Celsius, much of the land in the tropical and subtropical latitudes may become unproductive and depopulated, and inundated coastlines are common throughout the world, 60, with Scandinavia, the British Isles and New Zealand identified as potential lifeboats. Using the perspective of the Gaia hypothesis, 6, Northern Canada, Russia, Scandinavia, New Zealand and the British Isles, along with mountainous regions at lower latitudes, may remain habitable through the persistence of agriculture and may therefore act as lifeboats for populations of humans. Alternatively, a protracted energy descent following the passing of peak oil, combined with the effects of climate change, can also lead to different future scenarios including lifeboats, 61,62, which is a most pessimistic scenario, describing severe climatic changes combined with economic collapse leading to general decline in societal complexity, with isolated, localized pockets surviving as the indicated lifeboats, and is the most closely aligned with the scenario posited in this study. It may be possible to control a power down of global society as a preferable pathway to that of economic and environmental collapse. 56. The power down would comprise a concerted, global, long-term effort to reduce per capita energy and resource usage, equitably distribute resources and gradually decrease the global population, including the possibility of building lifeboats through community solidarity and preservation. 1.3. Decomplexification and nodes of persisting complexity. 1.3.1. Decomplexification. A robust assumption based on historical events and behaviors, 28,30, is that future changes may reduce or reverse certain fundamental measures of the condition of global civilization, including, but not limited to, total energy and resource use, systemic interconnectedness and rate of economic growth. The terminology of socio-political, societal and technological complexity, 30,31, is a useful framing that summarizes the collective state of global human civilization and allows the definition of a concept labeled as decomplexification. Decomplexification is defined as a condition in which the overall complexity of human societies at global scale would undergo a large and broad spectrum, i.e., affecting all parts of societies, technological systems and environments, reduction. Although this concept is central to this study, it is not defined in detailed terms, nor is it quantified. Instead, it is applied as a generalized description that captures a slowdown, cessation or reversal of the trends that are characteristic of recent civilization, notably, the exponential increases in multiple parameters, i.e., the great acceleration, too. At the highest level, the cause underlying such a decomplexification is the nexus of trends and phenomena described in section 1.2. It is not possible to be more specific about the causes that could potentially result in this occurring, but some possible modes of behavior for its occurrence can be described in more general terms. Decomplexification could feasibly occur as a discrete, short-duration event, 12,13, as a more prolonged, gradual and long-term process, 63, or potentially as a hybrid of both these types of events. These are described in more detail below. Seneca type. This would likely result from a discrete initiation event or phase for which there are no significant signals of the coming disruption and would lead to a rapid and profound decomplexification, potentially on the order of less than 1 year's timescales, 12,13. Long descent type. This would likely result from a combination of factors over a longer time period, and so would not be attributable to a singular initiation event and would likely be more gradual and incremental in nature, potentially on the order of years, decades timescales. A hybrid of these might be decomplexification with a prolonged, gradual and non-discrete initiation but which accelerates through the emergence of factors that gain a momentum through gradually strengthening enhancing feedback mechanisms and or cascading events, leading eventually to an abrupt Seneca-type event that results in the loss of remaining complexity. Any decomplexification process, whether abrupt in duration or as a result of a more prolonged reduction, would likely be heterogeneous in its progression. Neither the nature of any such changes, nor the behavior of human and natural systems during any such period of disruption can be predicted at any spatial or temporal resolution, but some broad assumptions about possible system behaviors and end states can be considered. The severity and consequences of this reduction would be highly dependent on multiple complex factors such as the exact starting conditions at the initiation of decomplexification. This process can, however, generally be assumed to result in significant changes to the fundamental extant organizing principles of global societies and, likely, the greatly reduced availability of energy and resources, systemic interconnectivity, mobility and size and distribution of populations, i.e., up to the severe catastrophe trajectories, 64. 1.3.2. Nodes of persisting complexity. Building on decomplexification, this study introduces the concept of the node of persisting complexity as a distinct alternative to the lifeboat's concept. This is of importance because the term lifeboat has the potential for controversy and to be politically charged due to potential for links with narratives related to future immigration controls and nationalism. This study instead seeks to explore possible and likely, qualitative, system behavior arising from a global decomplexification event. This will be based on a consideration of what geographical locations, nations, may retain some level of complexity, i.e., an appreciable fraction of current levels, during and after a decomplexification event, i.e., to become nodes of persisting complexity. This will require that several different characteristics and factors, labeled as favorable starting conditions, be considered in conjunction, in order to identify the areas that have the highest likelihood of retaining complexity during the course of a global evolution to an overall less complex state. It is noted that the nature of complex systems means that the final system states, i.e., after a global decomplexification event, cannot be predicted with any degree of certainty or granularity. However, the initial starting conditions can have a significant influence on final system states, so favorable starting conditions are considered to be a reasonable metric for this study. The central underpinning concept of this study therefore differs from the conjecture in other studies that certain locations may be preserved as lifeboats through deliberate action, i.e., by governments or other groups. Instead, the formation of any node of persisting complexity would be through system behavior arising from certain starting conditions, i.e., is an analysis of an evolutionary process that would occur largely outside of direct human control. This description has some similarities with the regenerative bioregions concept, 65, in which future localized populations may persist through their overall biophysical demands matching regional ecological conditions and carrying capacities. 2. Materials and methods. 2.1. Aim and objective. The aim of this study is to identify a short list of nations that have natural and anthropogenic favorable starting conditions such that they may have a propensity to form nodes of persisting complexity in a hypothetical future global decomplexification event. The objectives are to define and apply a simple semi-quantitative methodology to screen an existing dataset of nations in order to generate a shortlist of the strongest candidates in terms of their favorable starting conditions. Undertake an initial qualitative analysis of each these shortlist nations in order to characterize their unique features and analyze their potential to form a node of persisting complexity, and analyze the features identified to ascertain what features and characteristics may be applicable in the contemporary world to increase the resilience of nations, and other geographical regions, that do not currently have favorable starting conditions. 2.2. Approach. As noted above, the first objective of this analysis is to define and underpin a short list of nations which have inherent natural and anthropogenic characteristics that in combination are likely to comprise favorable starting conditions. This shortlist will need to take account of the factors that are of the greatest relevance to the potential nature of a decomplexification event to identify which conditions may interact with such an event to give a higher probability of allowing a degree of complexity to persist. The methodology for the identification of shortlisted nations is based around the extrapolation and further analysis of the outputs of the University of Notre Dame, Global Adaptation Index, ND Gain, 66, study. This is a study that considers a range of factors relating to the potential for climate change to disrupt different nations around the world. It gathers and processes a range of different variables to generate indicators of vulnerability to climate disruptions and readiness to mobilize adaptive actions. The overall output of the study is a combined score for each nation in the world and a ranking of nations according to proneness to climate change. Table A1 in Appendix A outlines the ranking of the highest scoring nations, and Table A2 and Table A3, in Appendix B and Appendix C, respectively, lists the 45 indicators used in the calculation of the ND Gain Index. The study is considered to be comprehensive, robust, and the data is open access, so it provides a strong basis for the analysis undertaken in this study. However, it does not account for several factors which are specific to the analysis of favorable starting conditions/nodes of persisting complexity. Therefore, additional semi-quantitative screening is applied to the top 20 least vulnerable nations, 66, to generate a final shortlist of 5 nations using 3 additional analytical measures that pertain specifically to the decomplexification scenario. For each of these 3 measures, an analysis is undertaken based on a semi-quantitative scoring system that is combined with the ranking provided by ND Gain to produce a shortlist of 5 nations with the highest favorable starting condition rating. These nations are then taken forward to the next stage of more detailed qualitative analysis, in Section 4. Table 2 describes the additional analytical measures and the basis for the scoring applied. The semi-quantitative/subjective nature of the three further analytical factors means that a scoring scale with only 5 gradations, i.e., which is reasonably imprecise and approximate, is deemed to be appropriate. This first stage of the further analysis is intended to be a general appraisal of the situation of a given nation, and the summation of the scores for these additional analytical measures, in combination with their ND gain rating, is intended to draw out a short list of those nations with generally greater favorable starting conditions. It is noted and acknowledged that the analysis applied is simple and superficial in nature and does not attempt to apply a rigorous analysis using a range of quantifiable variables. This approach is deemed to be appropriate for the analysis being attempted here. This is primarily because the nodes of persisting complexity that this study postulates are proposed to form through evolutionary complex system behavior, i.e., partially or largely outside direct human control rather than as a direct result of human action and agency. Such systemic behavior is inherently highly complex and unpredictable and dependent on a large number of interconnected variables. Therefore, a detailed analysis that attempts to make statistical or other predictions of system behavior would not be robust or could only be attempted using multi-parameter modeling approaches such as system dynamics, which, even if built to account for a large number of variables, would likely only be able to make estimates of broad modes of system behavior, which is what this analysis does. Therefore, a simpler, high-level approach that makes a low-resolution analysis of key features is proportionate for making a very macro-scale, low-resolution, i.e., at global and national scale, assessment and offers a robust basis for further qualitative analysis of potential nodes of persisting complexity. 3. Results. The application of the scoring mechanism outlined in Section 2.2, along with information underpinning this analysis, to the top 20 least vulnerable nations, as identified by ND Gain, 66, is presented in Table 3. This identifies the 5 nations with the most significant favorable starting conditions, which are then taken forward for more detailed, individual discussion in Section 4. Table 4 shows the calculation for the favorable starting conditions rating for all of the nations that scored more than 10, note not inclusive, i.e., those with the favorable starting conditions for the potential formation of nodes of persisting complexity. 4. Discussion. The crucial features common to the nations that scored more than 10 in the further analysis, and therefore having favorable starting conditions, are that they consist of islands, island archipelagos or island continents located at temperate latitudes with strong oceanic climatic influence. We note that Iceland is located at subpolar latitudes but has a climate buffered by the North Atlantic Gulf Stream/North Atlantic Current and so has characteristics of a landmass located further south, and Australia encompasses multiple climatic regimes due to its physical size, but includes a significant area with a temperate oceanic climate, principally the island/state of Tasmania, refer to Section 4.1. Nations and geographical regions with these climatic characteristics have a relatively low degree of temperature and precipitation variability currently and therefore would remain this way at the start of any decomplexification process. These locations would therefore also have the greatest likelihood of relatively stable conditions being buffered and persisting in response to climate change scenarios for the 21st century. By contrast, geographical regions in the tropics and subtropics are likely to suffer some of the largest changes in climatic patterns and at the earliest stages of projected climate change, 73,74,75. The continued viability of large-scale agriculture is more likely in any regions with existing areas of rain-fed, high-quality and fertile soil that is at lower risk of erosion and degradation due to the buffering of potentially warmer, stormier and more generally unstable future climatic conditions. Alongside agriculture, access to domestic sources of energy is required to support the continuation of fundamental societal functions and therefore support the formation of nodes of persisting complexity. For example, renewable electricity generation capacity could permit the ongoing operation of crucial infrastructure, for example, communications networks, pumping and treatment of water for irrigation and supply and manufacturing capacity, that would be necessary to support key capabilities. It is noted that highly complex technological systems such as power grids are reliant on technical knowledge and physical components, the provision of which is at least in part via highly specialized manufacturing and globalized supply chains, which is a key vulnerability. 76. In the event of a failure of these systems at global scale due to a decomplexification event, the viability of the ongoing operation of large electrical systems exploiting renewable energy systems or the development new sources, for example, drilling new deep hydrothermal wells, could potentially be in doubt. For the purposes of this analysis, it is assumed that grids could be maintained at some level of functionality through domestic manufacturing capacity. We also assume that other import dependencies of domestic industries including fertilizer or farm machinery can be discounted by assuming that a sustainable intensification of agriculture would be adopted in the event of a decomplexification event, or substitutions of key resources would be possible. The nations discussed in the following subsections are currently net importers of liquid hydrocarbon fuels for transport and other purposes, for example, as described by 77, in the case of Iceland, either because they do not have significant indigenous liquid hydrocarbon reserves, Iceland, Australia, Ireland, or have substantially depleted their reserves, New Zealand, United Kingdom. The technologies to use renewable, or nuclear, electricity to generate synthetic liquid fuels have been developed but have not yet been deployed at scale, 78, so it is assumed that this technology would also not be available following a decomplexification event. The following discussions therefore disregard the use of large volumes of liquid fuels for purposes, such as mass road transportation and aviation, and other primary fuels for large-scale industrial applications, such as cement manufacture. This assumes that in a global decomplexification event, large-scale mobility within and between nations, and the impetus for ongoing mass production of certain commodities, would reduce significantly. Electrical energy at either national or more local scales for essential functions as outlined above are instead assumed to be the priority. 4.1. Discussion by nation. Table 5 contains further detailed analyses of each of the 5 nations identified in Table 4. For each nation, the analysis is divided into the following: energy resources, climate, agricultural resources and other factors, and an overview of the national situation with regards to potential for formation of nodes of persisting complexity. The information is presented in bulleted format for ease of presentation and comprehension. 4.2. Sustainability and resilience lessons. This analysis of nodes of persisting complexity would be of limited value if it were simply a dispassionate analysis of what parts of human civilization might survive a major, global-scale decomplexification in relatively unscathed forms. Such an event would be bleak, tragic and history-altering when the loss of life, knowledge and cultural achievements, which would inevitably be attendant to such scenarios, are considered. As such, this analysis is carried out with the intent to aid the understanding of what contributes to making such events possible or probable and, therefore, to act as a component of the feedback, which may reduce the risk of them occurring. The analysis undertaken in Section 3 highlights that certain nations have particular characteristics, favorable starting conditions, that may maximize their potential to form nodes of persisting complexity. These characteristics are inherent to these locations, but there may be scope to apply aspects of these characteristics, or the benefits they naturally confer, to other locations that do not naturally have them. The application of learning from the nodes of persisting complexity analysis may be possible through actions local to nations or global regions, and/or through global-scale actions. Some of these may be already underway, or may be things that are not yet happening, but which may be feasible in the future. The following subsections discuss the favorable starting conditions in turn with reference to how they may be applied. 4.2.1. Future climatic conditions. Anthropogenically caused climatic change has the potential over the coming century and beyond to exacerbate conditions in regions already experiencing climate stresses and, in time, to significantly reduce the habitability of whole regions, for example, by jeopardizing reliable rain-fed agriculture. 75. The changes will be subject to complex local factors, i.e., geographical and cultural features, but there may be several degrees of freedom/generalized actions available that could potentially be undertaken to reduce vulnerability to these future climatic changes. At the global national level, the minimization of risks to regions that do not currently have benign climatic condition and/or which are unlikely to have resilience to changes may be best achieved through the international efforts to limit and mitigate greenhouse gas emissions. Given the uncertainty surrounding the scope and effectiveness of these international emission reduction schemes, efforts at the national-local scale may potentially be more effective. These may include the variation of agriculture to adapt to changing conditions, including diversion from industrial monocultures towards widespread application of techniques such as permaculture. 62. Measures to minimize the vulnerability of soils to erosion under increased storminess and civil engineering to adapt to changing precipitation patterns, for example, construction of reservoirs. 4.2.2 Carrying capacity. Prior to the modern era, human societies were predominantly reliant on local/regional environments for key resources, for example, food and metal ores. Constraints on the availability of localized resources, i.e., carrying capacities, were one of the main motivations underlying the expansion of historical nations and empires. 5. Colonialism, industrialization, and the globalization of supply chains has since reduced/removed the need for many nations to be self-reliant. This trend has increased global resilience to localized resource constraints whilst global resources remain plentiful, i.e., overall surpluses can be exported as needed, but has also increased overall global vulnerability to decomplexification. Where nations have become reliant on global supply chains, their ability to utilize local resources may be degraded and/or local populations may have expanded per capita resource use beyond the local carrying capacity. This may result in a high degree vulnerability to the reduction or cessation of externally supplied resources. There would therefore be significant benefit in nations assessing alignment or mismatch with their local carrying capacity, now and in the future, based on projected changes in population, including from any potential large-scale inward migrations. This could allow for the planning and implementation of measures to decrease vulnerability. This could include increasing the development and use of local resources, for example, agricultural land and water resources, even if not currently the most cost-effective solution, reduction/elimination of reliance on resources/products that cannot be produced internally, for example, agriculture reliant on imported fertilizer, and measures to decrease per capita resource usage. Such efforts could have the dual effect of reducing global resource consumption in parallel to increasing the resilience of regions and nations to global-scale events such as decomplexification. 4.2.3 Indigenous and resilient energy supplies. Energy is one of the metrics comprising carrying capacity as described above, but is so fundamental that it warrants separate consideration. This is because modern technological societies are wholly reliant on a continual supply of energy, in primary form and as electricity, to maintain the functions that underpin complexity, for example, supply of water services, logistics networks. The fossil fuels that supply the majority of the world's primary and secondary energy at a global scale are very unevenly distributed and, as such, are globally traded/supplied commodities. Therefore, nations that are reliant on imported energy, due to supply or economic factors, could be made highly vulnerable in a decomplexification event leading to a cessation of large-scale energy resource distribution. 50. Renewable energy resources are inherently more evenly distributed than fossil energy resources, and most nations will have access to some renewable resources. Therefore, the development of renewables infrastructure would provide resilience to much of the world to interruption of global energy flows. Even if the amount of energy that could be supplied via indigenous renewables infrastructure would be relatively low in comparison to that supplied by fossil fuels via global supply chains, some continued availability of energy may provide resilience, i.e., by allowing vital functions and therefore a degree of complexity to be sustained. 4.2.4 Dependence on global supply chains. As described in the previous subsection, modern societies are wholly reliant on technological systems, and these are in turn as reliant on the availability of manufactured items, i.e., parts and components. The capitalist economic system that has become dominant globally has led to global manufacturing becoming largely consolidated into a limited number of nations with favorable economic conditions, with low-cost logistics providing global distribution. 5. This situation potentially makes a significant number of nations with limited and/or inflexible manufacturing capacity vulnerable, i.e., a decomplexification event may decrease the local availability of manufactured items. The development or modification of a manufacturing base that could reliably supply key components necessary to the continued operation of fundamental systems, for example, power networks, water supply infrastructure, may provide some degree of resilience against a reduction in the global availability of such items. Even if the local manufacturing capacity were limited and able to only produce relatively crude/simple items, this may provide resilience, i.e., by allowing vital functions and therefore complexity to be sustained to a degree. 4.2.5 Over-reliance on high levels of complexity. Modern globalized society is characterized by high and continually growing levels of complexity, socio-political and technological. This has resulted from deliberate deployment of complexity to solve problems, i.e., increasing crop yields to feed growing populations, and as a self-reinforcing emergent property of complexity itself, for example, development of computing technology leading to the Internet. The deployment of complexity as a problem-solving strategy has become vital to the fundamental functioning of modern societies, for example, provision of reliable food supplies, but it leads to a vulnerability in that societies become reliant on its continual smooth functioning and growth. This vulnerability grows as complexity increases and more societal functions become reliant on underpinning complexity. Although it is likely to be difficult, practically and politically, to deliberately slow this trend and/or revert to less complex structures, efforts to seek solutions to fundamental problems that are inherently simpler may provide many nations with an enhanced resilience against the failure of complexity and other major risks. Examples of such efforts would include building local renewable energy systems in favor of gas-fired generation capacity requiring global supply chains, or a reduction in water demand in favor of building large-scale desalination infrastructure, such as that achieved in Cape Town in 2017-1898. 4.3 Long-term perspective. Given the human predicament and the challenges of seeking an effective means to navigate a safe path through it, a long view of humanity's situation that considers civilization in a cosmic perspective may be useful. Modeling the complex feedback loops inherent to the interaction between theoretical exo-civilizations, resource harvesting technological civilizations equivalent to global human civilization, provides a generalized context for the Anthropocene, 99, which indicates that any civilization intensively exploiting the resources of a closed planetary system will inevitably generate severe perturbation, i.e., through excessive entropy export to the surrounding environment, of its host system. The emergence of resource-depleting, self-destructive systems akin to the superorganism, 1, may be a thermodynamic inevitability, 4, where intelligence evolves in a planetary environment with an excess of resources, and therefore may be a potential solution to the Fermi paradox, i.e., a great filter. A slight variation of this scenario, 18, that may also place the trends of civilization in perspective suggests that evolution may produce species with instincts and intelligence sufficient to build the tools to access and exploit the accumulated energy sources of a planetary environment, but may be less likely to produce species able to build these capabilities and also to foresee the long-term consequences of the rapid depletion of a large resource endowment. 52. Given this perspective, the situation in which humanity finds itself currently may not be unique or unusual and may even represent something of an inevitability. If this is the case, the biggest challenge facing humanity may not be how to curtail the period of rapid growth after evolving the means to exploit a resource-rich environment, which evolutionary processes will equip intelligent species with tendencies to do. It may instead be long-term survival after the bottleneck of collapse that becomes a high-probability event in such circumstances. The nodes of persisting complexity that are the subject of this study could potentially be one of the factors in such long-term survival. 5. Conclusions. Human civilization underwent increases in socio-political complexity since the agricultural revolution, ca. 100 centuries ago, the Industrial Revolution, ca. 2 centuries ago, and with exponential characteristics as part of the Great Acceleration, 2, starting ca. 70 years ago. This generally has been characterized by phenomena such as large increases in population, energy use and interconnectedness, and has resulted in increasingly extensive and severe perturbation of the Earth system and the biosphere. This perturbation has resulted in a wide range of effects and feedbacks on global human civilization, including, but not limited to, climate change, increased risk of pandemics, ecological destruction, manifesting as a sixth extinction event, and growing risks of systemic instabilities. In combination, these effects place complex human civilization in a precarious and perilous position with regards to its future, the risk of an uncontrolled decomplexification event, a systemic reduction in the overall complexity of civilization at global scale, occurring may be increasing. Decomplexification has previously been described in the scientific and popular literature as collapse, or alternative descriptors including the Olduvai collapse and the Great Simplification, which may take place through various rapid or prolonged mechanisms. The concept of lifeboats has also been previously presented as a phenomenon that may emerge from decomplexification events and generally describe geographical locations that have capacity, by virtue of natural features and/or potential for human action, to avoid the most egregious effects of climate change or other global events and therefore maintain significant populations. This study introduces an alternative description and narrative in the form of the node of persisting complexity. These are defined as nations that may have certain characteristics, favorable starting conditions, that may feasibly allow them to retain localized, higher levels of societal, technological and organization complexity. A key difference with preceding narratives is that nodes of persisting complexity would form through evolutionary system behavior, rather than through any direct human agency. The methodology for assessing which nations have the potential to form nodes of persisting complexity utilizes the outputs of the University of Notre Dame Global Adaptation Index (ND-GAIN) study, which assessed and ranked all nations in terms of vulnerability and readiness to future environmental change. The ND-GAIN ranking was screened against additional semi-quantitative measures specifically related to the nodes of persisting complexity concept to generate a shortlist of 5 nations: New Zealand, Iceland, the United Kingdom, Australia, Tasmania, and Ireland. Each of these was then further qualitatively assessed for their individual, local scale, primarily energy and agricultural, characteristics. This identified New Zealand as having the greatest potential to form a node of persisting complexity, with Iceland, Australia, Tasmania, and Ireland also having favorable characteristics. The United Kingdom presents a more complex picture and potentially has less favorable characteristics overall. The analysis of the possible systemic evolution of global complexity is by itself of limited potential value, so this study applies the analysis of the nodes of persisting complexity to identify potentially useful insights for enhancing resilience for nations that do not have the natural confluence of favorable starting conditions. This analysis identifies that actions that may provide the means to address the interlinked factors of climate change, carrying capacity, indigenous energy and manufacturing capacity and the over-reliance on complexity might provide the greatest resilience against future decomplexification. Overall, the human predicament of exceeding global environmental limits, creating unmanageable and increasingly ineffective complexity and perturbing global life support systems may be typical of any energy and material resource harvesting civilization in a constrained environment. In this context, nodes of persisting complexity may provide the greatest opportunity for human society to retain technology and organization into the longer term.